This video is all about alternators and dynamos. They both use magnetic fields to produce electric power. Ships, cars and motorbikes use alternators to charge their batteries. Toys, power tools and bicycle lights use dynamos. To understand alternators and dynamos, we need to know about alternating and direct current. In direct current, electrons flow in only one direction, whereas in alternating current they constantly change direction. So you may want to watch this video first. In this video, we're going to look at how a change in magnetic field is used by an alternator to generate an alternating current, and a dynamo to generate a direct current. That's pretty easy to remember. A for alternator and alternating current, and D for dynamo and a direct current. Before we start, you should already know that when a conducting wire passes through a magnetic field, a potential difference is induced in the coil of wire. If the wire is a complete circuit, then a current is induced. Whether we induce an alternating or direct current is to do with these rings here, called commutator rings. This is an alternator, because the wire coil is connected to the commutator rings that are complete, whereas seen now, there is one split ring commutator. This is a dynamo, and so induces a direct current. When the wire coil passes through the magnetic field, a potential difference is induced. It's important to see this part of the wire coil always connects to the first commutator, and this part of the wire coil always connects to the second commutator. When the wire coil cuts the magnetic field horizontally, the potential difference is a maximum. As the coils carry on moving around, the potential difference decreases until the coil is completely out and not cutting the magnetic field at all, and so the potential difference drops to zero. As the wire coil keeps moving around and starts cutting the magnetic field again, we get a potential difference once more. Because the two sides of the coil are now moving in the opposite direction to what they originally were, so the blue wire is now moving down and the red wire is now moving up, the potential difference has reversed direction. It's now negative. Hence we have alternating current. So let's now look at the split ring commutator seen in dynamos. The blue side of the coil is moving up and starts off connected to this half of the commutator, and the red side of the coil moving down starts off connected to this half of the commutator. The potential difference graph looks like this. So maximum potential difference when the coil is cutting the magnetic field like this. And as the coil rotates out and isn't cutting the magnetic field anymore, we have a zero potential difference. The big difference is what happens as the wire coils keep rotating. The side of the coil moving down is still connected to the left half of the commutator, and the side of the coil moving up is still connected to the right half of the commutator. So the part of the coil changes which commutator it's connected to, but the commutators stay the same, left side moving down and right side moving up. The direction of the potential difference and current do not change in dynamos, hence the bouncy graph that always stays positive. This is what one complete rotation looks like on each potential difference graph. Let's finish by quickly looking at how these graphs can change. If we increase the size of the magnetic field, then the size of the current increases. This also happens if we increase the number of turns on the coil, or the area of the coil, and if we increase the rotation speed of the coil, then we increase both the size and the frequency of the current. So there we have alternators that generate alternating current due to having two commutators, and dynamos that generate direct current because of having one split commutator.